Okay, let's give you guys some more practice. So try to explain to yourself why you can't use the integral test to determine if this series will converge or if this will diverge. So try to explain to yourself why you can't use the integral test. So press pause and have a go. Okay, so if you look at the theorem for the integral test, it's saying that it needs to be continuous, positive, and decreasing. Well, uh, if you look at y equals x squared, it looks something like this. Well, it needs to be decreasing. So it needs to be going downhill. But here, x squared is it's increasing. So in order for you to perform this integral test, it needs to be continuous. So you can't have a break in the function. So you can't have a break in the function. It needs to be continuous. It needs to be positive, meaning you can't enter the negative realm here. And it needs to be decreasing. So it needs to be decreasing all the time in order for you to perform this integral test. Well, y equals x squared looks like this. It's increasing. So the integral test won't work for this. Okay. So next one. So try to explain to yourself why you can't use the integral test to determine if this would converge or if this will diverge. So press pause and have a go. So again, it needs to be continuous, positive, and decreasing. So if you look at this thing here, so here you've got one block multiplying another block. So hang on. So your sine graph looks like this, and then e to the power of x looks like this, but e to the power minus x, it will look like this. So it will look something like this. So if you look at this thing here, this point here, at c, at c, sine of c will be 1. This thing here will be 1. 1 times whatever this is, it will jump up to here. And then at point, I don't know, d, sine d will be 0, and then 0 times this thing will be 0, so we stay there. Here at e, sine of e will be negative 1, will be negative 1. Negative 1 times this thing here, it will be, it will jump to somewhere down here. Hang on, bear with me. This thing here will jump down to here, and then this thing here jumps up to here, this thing here jumps here, this here stays at 0, so your graph will end up looking something like this. It will look something like this, bear with me. I'm losing my concentration. It will be somewhere here, and then so on. It will look something like this. And then in order for you to perform the integral test, it needs to be decreasing. So it needs to be going downhill all the time. Here is if you look at this point here versus this point here, it's actually increasing because it's going uphill. Even though on the grand scale of things, overall it's going downhill because of this e to the power of minus n. But if you look at on a microscopic scale, right here, around this region here, I don't know if you can see it, but around this region here, it is actually climbing. And if you really want to see that for yourself, then differentiate this, and then you can see that the gradient will increase somewhere in there. Okay, so and the reason why we demand it to be decreasing is because of this. When if you look at the proof for this, we require the function to be decreasing because somewhere in the proof we require the area underneath this function here. We require this area to be larger than these rectangles here. But then if you have something that's increasing, it can get confusing because the area, because if you look at this, here you've got a rectangle here, here you've got a rectangle here, but if you have a function that's increasing, then you can't, well, in the proof we demand that the area underneath the function must be bigger than all these rectangles. Well, if you look at this rectangle here, because it's increasing, this rectangle here now is bigger than what it should be. Well, if you look at the proof, you understand why. Hopefully, you understand why we demand that the function to be decreasing. Okay, so overall, you can't use the integral test on this. Okay.